Okay. Hello, everyone. My name's Jim. I'm a professor at Northeastern University. I'm also a PI at the U.S. National Science Foundation's Institute for Artificial Intelligence and Fundamental Interactions. I'm glad to see many familiar faces in the audience. I'm going to give two lectures, one today and one on Friday. And this one is sort of more of an introduction to make sure that everyone is on the same page. And the essential idea in this is that we're going to be thinking about field theory for ML. And, you know, way down the line, sort of on Friday, we'll take it the other direction and think about ML for field theory. Maybe before I get started, I should ask, we all love physics and we all love machine learning, but I'm curious, how many of you would classify yourselves first as a physicist? Okay. And computer scientist? Hi. One. Mathematician? Oh, Daniel might, yeah. And mathematicians. Okay, good. So we really have the sort of the diverse audience that Andre had suggested. For some of you, some of the things I'm going to say are perhaps a little elementary, but it will accelerate and get more advanced. But I'm going to try to keep everyone on the same page. So this is today's lecture, and there's going to be three parts to it. The first part is going to be asking the question, why field theory? A priori, it seems like field theory and neural networks might not have a whole lot to do with each other. Throughout, actually, these lectures, for me, in this context, machine learning means field theory, even though clearly machine learning means neural networks, even though machine learning, of course, involves more than neural networks. So this is really about a connection between field theory and neural networks. And we'll try to spend some time with this question, and then there's going to be two main technical parts to this lecture. One is about neural network statistics, and then the other is about neural network dynamics. And we'll take each in turn. So some of the things that we're going to talk about involve why we should even think about the statistics of neural networks in the first place, instances in which Gaussianity of neural networks is part of the story and how that relates to ideas in field theory. If Gaussianity is part of the story, you might ask if weakly non-Gaussian theories are also part of the story and what that means from a physics perspective. And then finally, we'll turn to some classic results in neural network dynamics. At the very end of this, I hope to mention something called feature learning. Feature learning is something that we'll hear about sort of throughout the week. I am not going to present the end-all be-all of this. I'll present briefly one story, but I'm trying to set up the other lecturers and speakers who might be talking a little bit about feature learning, and we'll talk about why that's important. Yeah. So to get started first.
Okay.
Yes.
Just before you get started, increase slightly the font so that people online can also.
Perfect. Yeah. Hi, everyone online.
Maybe double.
Double the size. Okay.
Or 1.5.
1.5. About 1 and 3/4.
Yeah.
Okay, good.
Great.
Online friends, since you're listening, is this better?
Yeah.
So first, just to get on the same page about some language. First of all, let's talk about a neural network. Wrong letter. A neural network. So a neural network, for the purposes of this lecture, is a map from RD to R. This map from RD to R, this R was chosen for simplicity. There is a great pedagogical tradition in quantum field theory, which is to say do scalar fields first, because scalar fields that from the perspective of Sidney Coleman in particular, who taught that way at Harvard, scalar fields include many of the most important insights that field theory has to offer before you ever have to worry about higher spin fields. So we're gonna take scalar neural networks throughout. The story generalizes very easily beyond this case, but I'm going to take this for simplicity. Okay. These neural networks have parameters. The parameters I will denote by theta. This is collectively meant to mean all of the parameters of the neural network. In certain cases, I'll give it a little subscript, meaning the ith parameter. Hopefully it's clear what I mean. And then there's some other lingo that we'll need, which is the input to the neural network, which I'll just take to live in RD. The output is phi theta, this function acting on x. And again, one can generalize beyond the scalar case if you don't want to live in R. There's the network itself. Which is some map from RD to R. Depending on the construction, you might demand that those maps have particular properties. And finally, there's the data. I'll call it sort of script D. Yeah. This is the data set. The entire, yeah, sorry. Maybe I should write data set, yes. So there's, and furthermore, I might be talking about the data in an actual learning context as opposed to the complete set of inputs to the neural network you might have. So the data in real world applications is a finite set, but the input could be, all of, there's one element in RD, but you might have things in the input that you're considering that are not actually in a concrete data set you're considering.
When you say maps, will you make any assumptions about being continuous, being differentiable, or being anything?
There's different assumptions that one can make, and different neural network architectures have very different properties. I'm going to remain pretty agnostic about it. I mean, in general, they'll be smooth and differentiable and so forth, so that we can learn. But famously, ReLU activations have this non-differentiable point. Normally, we don't worry about it because in learning, you don't actually hit it. But it's not essential to worry about what type of map site. I mean, this is just some sort of function that depends on parameters. So the question to start with is, what does a neural network predict? And this might seem, especially to people that have used neural networks in their research, like a very simple, too naive question. And the naive answer, which is technically a correct answer, but it doesn't tell the complete story, is that the neural network predicts for fixed values of the parameters theta and a fixed input x, it predicts phi theta of x. And you might ask, is phi theta of x close enough to dog or cat or whatnot? But it predicts phi theta of x. And this is too simple. I mean, it's technically correct, but it masks part of the story. It's too simple for two reasons, and those two reasons are dynamics and statistics. And I'm going to say more about both of these in just a minute, but the essential idea is that these parameters are evolving in time. And when you start your computer, the parameter is drawn from some distribution on parameters. So there's also some random draw going into the neural network prediction that is affecting it. So the first part of the lecture is basically to try to convince you that once we put these ideas on, a better version of this naive answer to the question, once we put these ideas on it, the field theory language emerges and is sort of automatic and forced. And that's the main takeaway that one should take away from this lecture that's coming in the next little while. Okay. So let's talk about dynamics. The key thing to keep in mind when we're talking about the dynamics of neural networks is that really we have a bunch of trajectories. So we have one in parameter space. So I have a trajectory. The parameter associated with that trajectory is always going to be t, the learning time. So you have some real parameters. And as the neural network evolves, according to some learning scheme, there's some trajectory in parameter space cut out by the learning dynamics. That's one trajectory. Because the parameters are evolving and you have this trajectory through parameter space, you also have a trajectory through output space. Namely, the neural network predictions are evolving. And if you'd like, you can also think about this in some sort of function space. Turn that into a function space. And this is phi theta of t, which is evolving in this space of maps that I'm not worrying too much about the details of those maps right now. Trying to stay general. Okay.
The
Yes.
modulus of theta is the number of parameters, right?
Yes, that's right.
And what's the difference between moving in parameter space and moving in function space?
Good. Normally when we talk about the learning dynamics, we talk about actually updating the parameters, and we'll talk about that in just a second. Indeed, the movement in parameters, because the neural network depends on the parameters, the outputs evolve, and this movement through function space, through parameter space induces a movement through function space. So these trajectories are all related. Normally, we think of learning as updating parameters, but my point is just that yes, there's this obvious parameter this obvious trajectory through parameter space, but it also induces trajectories through outputs. Yeah.
Same question on output space and function space. Is output space only on the training set or something like that? Or
I'm leaving it general for now. I mean, it is true the whole function is evolving, but as you're doing the learning and the whole function is evolving, all of the putative outputs for any x in the domain are evolving. But indeed, we always train on a finite amount of data. Okay. So maybe just to give.
Yeah, there are spaces that are properties.
Hey, Luis, how's it going? All right. So just to give a concrete example, there's something called supervised learning, where the data set D has the form x alpha, y alpha in RT times R, where alpha runs from 1 to the cardinality of the data set. So these are now concrete data points that I'm talking about. There's a ground truth label associated to every data point in the domain, and you might do something like have a loss function that is a sum of element-wise losses across the data set. It depends on the network prediction and y alpha, so forth. And the basic idea in supervised learning is that you have some ground truth. The network is making some prediction on the inputs, and you have some measure of error between the predictions of the network on the inputs and the ground truth, and you're just trying to minimize that. So a simple case is that L, for example, L might be L MSE. MSE for mean square error. Okay. That's one type of learning dynamics. And maybe to say one more thing about dynamics is that for another example, I have this little bit of board up here. You could ask, this is one type of, yes.
Just to interrupt you.
Yes.
What's the difference between supervised learning and just regression? Like you have a function with parameters and you give data to it.
I mean, in the language that you just said it, I don't know that I would draw such a huge distinction necessarily. And in particular, when I teach computational physics with a severe machine learning bent, I have them do linear regression and I call it a very simple neural network. But part of the point is that this is, if you'd like, this is regression in the context of function classes that can be universal approximators. So they're very expressive functions. So this is one example of a learning scheme. There's many other different types of learning schemes that might arise. We can talk about those. This is like how you set up the learning problem in the dynamics. But then you could ask what induces the trajectories through parameter space. And the most famous is gradient descent. Oh, online people, is this big enough or should I be bigger?
Still okay, yeah.
Still okay, good. And gradient descent basically is just the rule that you have this loss function. You have this loss function here, and you're going to update the parameters according to the gradient of the losses with respect to the parameters. So, there's some cost function L, and you follow it down. So this is the dynamics part of the story.
Shift the board.
Yeah, maybe I'll do that. This is new to me. I've had many types of whiteboard over the years, but this is a new one. Good. Okay. What's that?
People on the other side will wait.
That would be very nice. Yeah. Okay, good. So that's the dynamic story. Neural networks evolve. That should not be surprising. You know this. But something that you might not have thought much about is the statistics. What do I call it? Statistics. Ooh, here is board ends. Problem of being tall is that you reach above where the board ends. And the statistics story is also pretty simple. The neural networks evolve, but they evolve from a starting point. And the starting point, when you start your computer, involves drawing the parameters from some distribution, period. And if you restart your computer and you didn't set the seed, you get a different parameter, therefore a different function, right? And so squiggle in statistics means drawn from. So these thetas, these parameters, are drawn from some distribution on parameters. And what this means is that for some fixed theta draw, the neural network prediction is not fundamental. In the sense that it depended on one particular figure. Okay, good.
Jim, is this upon initialization specifically or?
Good. So right now I'm talking about at initialization. Generally, what we're going to talk about in a minute is that these parameter densities in principle evolve. So if you imagine, throughout these lectures, we'll imagine that we're not compute limited, even though we really are in the real world. So I'll let you imagine tracking the flow of the entire parameter density from the initialization parameter density all the way through learning. But indeed, at initialization, the initial parameters are some random draw. And so that neural network is not fundamental. And really what you should do is you should be computing some appropriate average over the different initializations to get at something more fundamental. Bigger, good, noted, thank you. So in particular, something that is more fundamental is the expectation over these different thetas of phi theta of x. So indeed, one can think simply at initialization. This is computing the expectation, the expected value of the neural network prediction on x across all different initializations. Okay, so there's no randomness coming from the draw. This depends not on a particular draw, but instead it depends on the distribution P of theta. Okay, so we would compute this, and this is how people compute it in the literature, by integrating against the parameter density. Similarly, you might be interested in the covariance. And these things are now integrating across the full space of all random initializations that you might have started with, weighted according to the probability density on parameters. And so the initial roll of the dice that one initialization of your neural network might have given you, we have integrated over all of these choices. And so just on fundamental grounds, these objects are sort of more essential, that if you weren't compute limited, these are the things that you would want to know on theoretical grounds. Okay. And the essential point is that already this thing here is, in field theory language, a one-point function. And henceforth, I will be using Brock-Ket notation for statistical expectations, just because we love field theory and we want to write it in this language. And second of all, this here is the two-point function. Okay. And so already we sort of have the essential points. We want to average over in the distribution across all of the different initializations of the parameters. We want to average across the neural network predictions and the products thereof. And these are one-point functions and two-point functions in physics language. And so, ML and field theory, or neural networks and field theory, seem to have something to do with each other. And that is the main point I want you to take away, that the statistics of the parameters is endowing the theory not with one particular neural network, but with an ensemble of neural networks that has correlators. Oh, yes, I can do this. Good. Can be taught. Okay, finally, yes.
That you will come with just the probability distribution, right? For which
Do you want me to make a comment now?
maybe I mean just
Sure. Part of the defining data of any time you start a neural network on a computer is how you draw the parameters of initialization, whether it be from an explicit distribution or whether it be some algorithm that draws that gives you some implicit distribution. This is always part of the setup. It's part of the defining data of neural networks, and so there's always a parameter density. You could ask various questions. How does the choice of parameter density affect the statistics? If machine learning is related to field theory, it turns out the normal way of thinking about field theory is about probability densities on functions, not on parameters. And so you might ask how the probability density on parameters, that choice is related to the probability density on functions. All of those questions are in the game. I'm just trying to stay as general as humanly possible right now. And the nice thing is that staying ultra general, we've already arrived at 1-point and 2-point functions. There's another question. Yes. Pardon? That's right. Yeah, that. I would encourage you to ask that question a little later or more, or on Friday when we'll be talking more about sort of the for field theory direction. But normally we talk about small field fluctuations in quantum field theory. If you have an equation that represents your field, right, like a neural network might, that's part of the idea here, then small fluctuations of the parameters will induce small fluctuations in the fields. Yeah, we're gonna get to all of that. Those are all the right questions. One of the questions that he asked was, can you write down some action? And we're going to get to that. Okay, and so maybe just to make a final comment in this section. So if we put statistics and dynamics together, because it's not just statistics and initialization or the dynamics of an individual neural network, the full theoretical construct is really an ensemble of neural networks flowing during learning. Okay. Well, the dynamics involves notions of trajectories and evolution, and the statistics involves notions of 1-point functions that capture the average prediction and 2-point functions that capture the covariance across the different distribution parameters. And therefore, you should put these things together. And so we imagine that we really have theta of t drawn from some flowing parameter distribution, p theta of t. And then you might want to talk about the time evolving 1-point function, x, which is the expectation value phi theta of x computed in the time-dependent parameter distribution. One second, let me make one more point. And then you might also compute the 2-point function t, xy as a function of t, that is phi theta of x, phi theta of y, evolving in this time-dependent density on parameters. Yes, sorry.
this P theta of T, you don't mean that, do you? Because P itself evolved.
Is
So
what?
you mean PT of theta?
You want me to,
In that, yeah.
you want me to write as a subscript? Yes.
I don't want the P of theta of T.
Yeah, I'm sorry.
Yeah, isn't that right?
Yeah, it is,
The,
it is,
the distribution of the theta is evolving with the.
yes, thank you, yes, absolutely. Yeah.
Good.
Okay, but so this language is really useful because first of all, it emerges from fairly general considerations with relatively few assumptions. I didn't get super specific about anything here. I just talked about dynamics and statistics of neural networks. And then there's an interesting object. If you were to ask, what might you like to understand about neural networks as they evolve? An interesting object is G1 of infinity of X, which is the mean prediction. I'll write it out in words, of an infinite number of neural networks as t goes to infinity, which presumably, if you've set up your learning problem well, is moving towards convergence of the learning procedure. Okay. And maybe just to say, that's great to say in theory. This is an object that is clearly of fundamental interest. The average prediction of an infinite ensemble of neural networks as you evolve towards infinite learning time, that sounds great. But in general, you would expect this to be totally intractable. And one of the points of this lecture, it's other people's work, not mine, is that there are cases where we actually know this analytically and exactly. And that is a surprise. That's a result from 2018, and I hope to explain that by the end of the lecture. I'm permitting. I think for this section, that actually concludes what I wanted to say. Let me just summarize and then I'll take questions. So just to say one more time, the neural network is a function phi theta of X, depends on parameters. Those parameters evolve, and they evolve from a randomly chosen starting point. So the fundamental theoretical object, I think many people think, is to consider the infinite ensemble of neural networks flowing as learning happens and to consider the statistics. And to ask questions about things like G1 and G2, which are intrinsically field theoretic concepts in a way that we can talk about. Yes, Andre.
So the infinite number of neural networks matters just for taking the average, right?
Yes, that's right. And in particular, if you wanted to do this concretely in a more general case where you don't have theoretical control, you could say, I've got a supercomputer and I'm going to take 1,000 neural networks, and you could estimate this via monochrome. Yeah.
So I guess the input is also a distribution. So I guess if you want to give some meaning to the translation function, the one function, you kind of need to consider this distribution.
I'm not. In general, you might also consider that distribution. People call that the data distribution. I'm imagining, first of all, that I consider this object as a theoretical object on the entire domain of the function, and that presumably it's getting trained with a finite data set. But indeed, that data set came from somewhere. Someone created it, and it is drawn from some distribution on data. Yes?
I think I understand this T here is like the same time variable as the theory or something.
No, that is crucially different. You could try to make that connection. I'm not going to these lectures. Generally, when I'm talking about field theory, I'm going to be in Euclidean field theory, so I only have imaginary time. All of the coordinates are on the same footing. I'm on RD. This T is the learning time. So this is when someone actually trains a neural network. This is the learning time, which is correlating with some actual clock time on a computer as the neural network is being trained. It's a different T than the one in Lorentzian field theory.
So you're using the different patterns of every
the way that I like to think of it, and we'll get to field theory stuff in a minute, is that indeed at any given time slice, I have a P sub T of theta. Thanks for the point. P sub T of theta, I have a distribution on parameters at that particular time slice. And because of that, I can define the correlators there. And so in some sense, I have a field theory at every time slice. So I would think of T as a flow in the space of field theories rather than thinking of it as the time coordinate of a Lorentzian field theory.
So if you think of it as another flow in space, field theories is a normalization.
Yes.
It's a time in that sense.
There definitely are stories relating that T to renormalization. Zohar has worked on that and is maybe going to talk about it in your talk. One thing that I think physicists are in perhaps a bad habit of is thinking that all flows are renormalization group flows, which is simply not true, which is not what you mean. So in very specific cases, it is a renormalization group flow. And there's another idea that's related due to David Berman, where he wants to think of Bayesian inference, where adding more data in computing the posterior is like a flow, is like the time coordinate t as you add more and more data. And he has mapped that onto Polchinski's exact renormalization group in a different context. So there are places where you can think of this flow in terms of renormalization, but in general, you need not, because general flows are not renormalization group flows.
I had an online question, if you can hear me.
Yes, sure, yeah.
So I might have thought that one quantity of interest is what we condensed matter types would call this, self-averaging question, which is to say, how does one particular set of parameters compare with the average over the ensemble of parameters? Because presumably the actual networks, right, you run the thing and you have one set of parameters which are going to be what you're going to run. So the fluctuations over theta.
Yes.
So are there cases where those are computable?
Yeah, so in the toy model that I mentioned, it is true that they have the time evolving neural network prediction for a fixed trajectory and fixed set of parameters. And if you so choose, it is also known how to compute the ensemble average. And so you can subtract them if you want.
But isn't that also a fundamental quantity of interest? If that wasn't small, if the answer depended on averaging over 1 million networks, then that's
yeah. That would be an implicit measure of the variance, which you might also try to compute directly via a 2-point function. But indeed, that is something that people are concerned about. So for example, in LHC applications, when people are interested in doing something called jet tagging, there's some variance over the different initializations, and people want to make sure that they get that under control so they can understand the systematics for particle physics. So indeed, one particular neural network, there might be a lot of variance in the predictions, and there's different ways to measure that exactly as you said.
Thanks.
Yeah. Sure, yeah.
Should I assume it depends on the initial ensemble that I choose?
Yes, it does. It does because, I mean, there's for every different starting point, there's some flow that is induced by it under a fixed learning scheme. And so the distribution on parameters at initialization affects the flow of the entire thing, which affects G infinity.
Well, but you hope that there is some loss of memory of the initial.
Yes, absolutely. You might hope that there is some loss of memory of the initial choice, and in some contexts, I think there are, although they're not coming to me immediately. Other questions?
Some second term you discussed about X and Y, so you want to define it a little bit more crispy by saying there is a training set which is included in the average to train, and then these X and Y are drawn from a separate set, basically. A validation set or some different.
Yeah, you can consider this object on purely theoretical grounds for any X and Y in the domain of the function. And then when you actually do learning, you might do a test train split. You might first of all have the entire data set, concrete data set that you're training with, that you're studying, some subset of which is trained data, another subset of which is test data. But if you know this thing or understand this thing for all X and Y's in the domain, you can certainly apply it to test sets and train sets.
So,
yeah, sure.
So all these functions are actually dependent on the data distribution also.
It depends. No, not necessarily, because just talking about them as just talking about them as X's and Y's in the domain of the function period, I don't have to talk about the data distribution that gives me a concrete training set. The concrete training set will of course affect the flow, but I am considering these as objects a priori that exist for all X's and Y's in the domain.
So the asymptotic part depends on the data, but
Exactly. You can talk about these things on the entire domain. How it evolves, of course, depends on the data, which depends on the data distribution.
The Y that you have in the supervised learning.
Yes, I'm sorry.
It's unfortunate.
These are related to some lectures I gave in Colorado last year, and indeed, this is unfortunate. This Y is not the same Y as over here. Yeah, apologies for that confusion. Thank you. I'm not going to talk about supervised learning for a little while. Yeah. A student complained about that last June correctly, and I apparently did not fix it. So I don't need this. That's right. Fancy blackboards. Okay. Any final questions? This is the end of the. This is the end of this part. Wide field theory of. If you get nothing else out of everything I say today and on Friday, the point is that 1-point, 2-point functions and generalizations thereof emerge naturally as fundamental quantities in machine learning, period, full stop, end of story. And then you can start to build up technical stories from there, which is what I'm going to do. But in some sense, I really didn't have to do anything. I landed on field theoretic language just almost immediately. And that's the point. All right. For all of this, yes, I talked about statistics and dynamics, but this was all in the context of why field theory. Now I'm going to get to beefier versions of the story. So this is statistics in depth. Yeah, I'm doing on time. Okay. So we're trying to address the question, what characterizes the statistics? The ensemble. And these can be encoded in the endpoint correlation functions. I'm often going to drop the subscript theta on the phi's just so I don't keep writing it over and over again. Networks always depend on the parameters. Okay, keep that in mind. And the way that we normally do this in field theory, one way to think about these things is in terms of a moment generating function. And the standard prescription is to have the g's, the correlation functions, or moments of this distribution. Whole thing d by dj at set j to 0. Those functionally pull down these copies of phi and just trivially reproduce the correlation.
All this carries an index t, right?
Yes, I can talk about this at all times. Whether you can compute it efficiently is another question entirely, but on theoretical grounds, all of this carries through. Okay. So then maybe to make the point, okay, I'm learning to love this. This is great. Maybe to make the point, I have just written this way, and you might ask, how do I actually write down a partition? And in particular, because I already wrote down one form for the correlation functions already, where the correlation functions were computed by integrating d of theta p theta, and the neural networks depended on these thetas. The neural network description is that z of j is equal to integral d theta p theta, e to the integral j of x, phi of x. Okay, yeah, there's a dx that I. And this, when you apply that d by dj formula, will literally reproduce the equations that I wrote a few slides ago, where the expectation is computed by integrating against p of theta. And this is the thing that's natural from the point of view of machine learning, because this data is in this functional form of phi, I should have said, is called the architecture, right? So this is actually some concrete function that you write down with parameters in it. The functional form is called the architecture. The p of theta is something that, as we talked about, you define. So this is something that the neural network always affords you. There's a beautiful paper in the 90s due to Williams where he computed 2-point functions concretely in real cases, and he does it by integrating against parameters, okay, which is not what physicists normally do, and that's part of the point. He does it by integrating against parameters, and this description is sort of automatic. But this is not what we normally do in field theory, right? What we normally do in field theory is the Feynman path integral. For example, mathematicians will famously quibble about this object and how to define it. I am not going to add anything new to that story today, but this is how we compute, this is how we understand partition functions in normal QFD1 when we take it in graduate school. And sort of this is this neural network description. And one of the points is that when I write these correlators, when I write it this way, I am agnostic about how I describe the expectation value. So you could understand that expectation value as an expectation value in some space of functions in terms of some sort of density on functions. Or if you have a functional form, an architecture for your field with some parameters in it, you could understand it in this way. So this is sort of the statistics agnostic version of a correlation function. This is what the neural networks sort of automatically give you. This is how we normally do it in QFT. And so should have given more room, because what I want to ask, are these two descriptions related?
The phi in the top equation has a little theta in the subscript.
Yes, absolutely.
And in the bottom one, I guess it doesn't, because you're integrating the whole phi, so that's the relation.
It need not have that, when you describe it in function space with some appropriate action and measure, you won't worry too much about the details of how to define the measure. You don't really have to worry about some implicit parameters that were there. That's right. Yeah, so this is the normal way we do it. We don't talk about architectures or parameters ever normally in field theory. This is a different way to do it from a neural network description. In some sense, they're just two different ways to define the expectation that defines the correlators. And you can just ask, are there cases in which they're related?
Just for the vocabulary, when you say architecture, you mean selecting a subclass of functions, right? From the space of functions,
yeah,
which is parameterized in a certain way by these thetas.
Yes.
And then you actually know what to do when you say integral theta, TF theta.
Yes.
Unlike the other case.
I think you are pointing out that because this is a normal integral, this seems obviously well-defined mathematically, and you don't have to have the worries that you have there. That's absolutely right. So Andre was making 2 points. Indeed, the architecture is the functional form. So you have heard of feed-forward networks, also known as multi-layer perceptrons or deep neural networks. You have heard of convolutional neural networks. You have heard of transformers, famously. All of these are architectures, which just means a concrete functional form with parameters in it. In this case, I do, in principle, on theoretical grounds, know how to do that integral because it's an ordinary integral. Yes?
I'll say this another way. So, I mean, if it were the case that these two z's were actually the same, right?
We'll get there, yeah.
No, yeah, you might get there, but I'm sorry. Right? So, if it were actually the case that those two z's were the same, then that would appear to require that your set P of theta was infinite set.
Yes.
And then you wouldn't have an ordinary integral. You would have some kind of measure integral.
Maybe that is true if you were recovering normal stories about infinite dimensional field theory. Indeed, it does require infinite neural networks of an appropriate type. You can ask a related question, which is, if you have a finite neural network that is close to infinite, yeah, but actually finite, what does that correspond to in this description? And one of the things that can be done, building on some work that Zohar did actually using something called the Edgeworth expansion, is there's an appropriate n parameter where n, as n goes to infinity, the number of parameters goes to infinity. At large n, you can compute the leading order correction in 1 over n to the action. So that's something that can be done. But indeed, how these finite dimensional field theories at nearly, in some very large limit relate to the standard story is part of the open question still. And I'm not going to answer that today. I can tell you insights I have, but I can't tell you crisp answers. Yes?
It's appropriate to say something about universal approximations here, then, have a finite number of parameters in theta.
Well, yes, good.
What kind of function can you make?
That is also part of the point, is that because as n gets big, these are getting, so neural networks appropriately chosen are universal approximators, which means that as you make n big and you go closer and closer to the infinite parameter regime, they can approximate arbitrary functions closer and closer and closer. So because of that, it's intuitive that you might map onto the natural infinite dimensional case here. But you can also just study these things in this description at finite number of parameters, finite but large number of parameters. So it's part of the story, but not essential. Yeah, this is great. I love that this is so interactive. Okay, so you can ask, one, are these descriptions related? But another perspective that is, I think, perfectly valid is just work in the neural network description. If you go, for instance, to the strings conference these days, which is something that people in my community like doing, half the talks are about field theory. And field theory is itself something that people are still understanding in different ways, deeper ways, etc. And the point is that you can define this using neural network data, and even if you don't know what the action is, in principle, you can express and compute the correlators. So you can get control over some of the field theoretic data, even if you don't know the action. Which to people in my community, the idea that there are field theories that are not defined by actions, where that's not the starting point, is very well known. That's very famous in the high energy theory community and also elsewhere. So, okay. Good. I'm starting to worry that I bit off more than I can chew, but that's okay. All right. So let me tell you about one version of this story. In this description, if you want to relate these descriptions, you might ask, are there particular limits where things are very well behaved? And Gaussian limits are one of the simplest limits you can get in statistics. So this is something called the neural network Gaussian process correspondence. And maybe I'll just exemplify it finally to have an example. I'll just do it in an example. Okay, so I'm actually writing an actual architecture now. Okay. Here's an actual architecture. Sigma is some nonlinearity that I'm going to leave general. Don't worry about it. And so here, the parameters 0. The set of thetas is these set of parameters, the input weights and the output weights. This is a single layer network with biases turned off. And one of the reasons I love this subject is that so many of the ideas just come so naturally. So I will just make the observation. Looking at this, this here is a sum of n independently and identically distributed functions. So what's happening in this sum? These parameters, sorry, I should have said that these parameters, we assume that we draw them IID. So because the parameters are drawn IID, if you think for a moment, you can convince yourself that everything in this sum is the same type of statistical object, but they're independent draws. Yeah, because the parameters are independent. And so this is some sum of n IID functions. Good. I have assumed in this parameterization that the variances of these parameters scale as n to the 0. And that's why I put this 100 n out front. And the essential point is that this is the context of the central limit theorem. So eventually I'm going to write out a grace. See how long it goes. Actually, maybe I'll just state it here. I'll pull this down. What's happening? So here's the NGP correspondence. Oh, I have more to say. All right, so the neural net, sorry about that. So the NMGP correspondence is basically saying is that as n goes to infinity, and I should have said that in this context, this is a single layer neural network, and it's called the width. The width. So as the width goes to infinity, phi is drawn from a Gaussian process. And what that means concretely, as n goes to infinity, phi of x is drawn from a normal distribution on functions with some mean function, the 1-point function, and some kernel that is related to the 2-point function, the 1-point function. So this is G1 and G2 data in field theory language. So because of this, because as n goes to infinity, these neural networks are Gaussian distributed, what that means is that, and, this whole description so far is the tier, but what it means is that e to the minus s is a Gaussian. And so looking at my time.
This is for an untrained network or with MSC loss. This is for an untrained network or with MSC loss.
Yes, that's right. Zohar is raising the question, when does this hold? We'll ask that more generally. During training, non-Gaussianity will in general be broken. Sorry, Gaussianity will in general be broken. There are some cases like MSE loss where Gaussianity is preserved during training. At initialization, it is much more regularly Gaussian. Yes.
I have a question about your architecture. Should the sum over J not be inside of the nonlinearity? So not linear layer, then.
Yeah, sorry. I'm so used to doing Einstein summation that I indeed I should put my sum on J here. Yes, the sum should be inside. Thank you.
There's no J outside.
Huh?
There's no J outside.
Yeah, the J's inside. That's right. Exactly. I'm so not used to writing sums because I always do Einstein summation, but when I do, I do things like that. Thank you.
Are there any assumptions on sigma? I mean, initially, I think this was proved for activation functions which are flat and then like.
I mean, you need to make sure that in the limit, the assumptions of the central limit theorem hold so that the appropriate correlators of these things themselves are finite moments and so forth. Those are the essential assumptions. One can be super precise about that. The point that I'm going to make about generality is not actually about sigma, it's about different architectures.
So I think the question I have, so this NNGP correspondence is not dependent on the universal approximation property of the sigma.
No, it's not. Yes. Yeah, that's right. Okay, so in my notes, and I'll actually share my notes, this is based in part on some lectures I gave last year that I can send. I actually do a concrete computation, but in the interest of time, I'm just going to tell you how it goes. So for example, if you wanted to take this architecture and do the 2-point function, compute the 2-point function, or alternatively the 1-point function, let's talk about the 2-point function. This is phi of x, and you just pick phi of x times phi of y, and you put it under an integral over all of the parameters. Part of the construction is that I'm assuming IID here, but for any given concrete realization, I need specific distributions for this and this, and then I just have some integral, right? And it might be a little bit of a pain to compute that integral, but actually in many cases you can do it exactly, and you can know the exact 2-point function, which is not something we normally have in field theory. I'll make that point. Can compute G2 of xy and G1 of x in examples using this parameter space description. Sometimes you can do it exactly, meaning you can evaluate the integral, no perturbation theory required. Good. And part of the point that is relevant, the reason why I mention it, first of all, I'll say that in many cases, the 1-point function is 0. So if the output weights in a network are chosen such that they have mean 0, which is a very common assumption in standard visualizations, then the 1-point function is automatically 0 because as you average over that output weight, you get 0. Right? So it's very commonly the case that the 1-point function is 0, and then it's just a question about computing the 2-point function. And coming back to this question about the action is integral ddx dy 5x into xy inverse 5. Okay, where this inverse is defined as such.
That's what you said about the activation function, by the way.
Yeah.
Continue.
So there's different ways that you can ask. Part of Andre's question was how general is this story? I'm going to talk about another direction in a second, which is for very different architectures. But to specify to like fully specify the architecture, you have to specify the activation function. When you do the 2-point function computation, you'll find that one of the important objects is the 2-point function of these things right here under those weights. Yes. And if you choose sigma unwisely, you can have things diverging, and then you don't have a Gaussian process. So basically, as long as the moments remain finite, which is a standard assumption of the central limit theorem anyways, that the things that you're summing are finite moment, you're in business.
But it can be discontinued. ReLU is allowed, for instance.
ReLU is allowed, and the answer is known due to work of Cho and Sol from like 2010. Okay, so at large n, you have a Gaussian theory. You can compute the 2-point function. The 1-point function is often 0. If it's Gaussian, the 1-point function and 2-point function determine everything. And so you completely know the theory. And you know the action's that. Okay. Let me come back to this question of generality. Andre wanted me to vary sigma. I want to vary something else. So a little bit of history. This work is originally due to the thesis of Radford Neal in the 90s, who was trying to connect Bayesian techniques to neural network techniques and understand how these things are related, because that's something people in computer science were interested in at the time. And what he did is he proved the correspondence for a single layer perceptron in the large n limit, in the large width limit. And around 2016, a variety of groups started asking, wait, can't I do it for this architecture? Does this architecture emit a large n limit? Does that one? What architectures emit large n limits that are Gaussian? And one way to rephrase this question in that light is, what really made it work in this example? And it's really just central limit behavior. Because of the attention paper, it's very common now to just say such and such is all you need. So it seems that in this context, central limit is all you need. And so in principle, any neural network architecture that involves summing IID stuff and taking n to infinity, such that the assumptions of the central limit theorem hold, gives rise to a neural network Gaussian process correspondence as n goes to infinity. Okay, and so in particular, to give you examples, NNGP architectures, name a few. So the one I just gave you was single layer feed forward neural network, and n is the width. But it's also true for deep feed forward neural networks, where n is the width. It's true for convolutional networks. Convolutional networks are used in image processing. They are the networks that it's used in image processing. They have channels and kernels that pass over the image and pick out local features. Here, n is the number of channels. Finally, for attention, which is what's relevant for transformers and large language models, n is the number of attention heads. And perhaps this is not surprising. The list goes on and on and on. There was a literature from 2015 to about 2020 where there were, I don't know how many, dozens of papers and maybe 10 to 20 different architectures where people studied this. But as far as I can tell, as a physicist who's an outsider, the answer is always the central limit theorem, and then you work out the details in any example. So this gives some sort of organizing principle for understanding neural networks in a case where you can compute the action. In this limit, you have both the action-based description and the parameter-based description. Both are available to you. And they're dual descriptions because they have exactly the same statistics. And notably, mathematicians rightly will complain about the path interval. They are much less likely to complain about Gaussian path intervals. Gaussian path intervals are much better behaved. Yes?
This n here, is that any relation to if I have n scalar fields, each one, when you say I, then each one has a different distribution.
This is a single component scalar field. You're wanting to consider like an ON vector model.
Yeah, is there any relation?
Great question. If you wanted to, notice that this thing here has an index. I could call this hi of x.
Yeah.
I could study the field theory associated with that. It's not necessarily going to have ON symmetry, but it will. This is n scalar fields here at the second to last layer before I do the output to the scalar. And indeed, that n you could think of as an ON. I should not call it an ON model because it doesn't necessarily have ON symmetry. It's a vector model. Yeah.
Jim, I had an online question.
Yeah, sure.
So I guess I'm confused by the following, which is I have a data set and I train, and if I look at late times in the training, even if my initial parameters were IID,
Yes.
I wouldn't expect the ending ones, right? Because there should be some convergence of flow because ultimately you're trying to optimize something. So when you say that this works, what is the magic? Is the wide limit somehow? Yeah, sorry, and I think you know what I'm confused about. How this connects to how?
I think I know exactly what you're confused about, and I can try to clarify if you'd like. This is a question that is very common. It was pointed out a few minutes ago that under certain assumptions, Gaussianity persists during training, but they're very specific cases. Yeah. That's a very specific case. And your point is basically that you would expect there to develop strong correlations between the parameters during training, yes?
Right.
And therefore, indeed, that will break Gaussianity. And part of the essential point here is that if you're, I think the perspective in the literature, as I understand it, is that we should think of Gaussianity not as the end-all be-all here, but a toy model around which to build our theory. And so, for example, if we're Gaussian at initialization, then the question becomes, how does training introduce correlations that are relevant for learning, but break Gaussianity? And so that non-Gaussianity story is actually the next part of the lecture. I won't have too much to say about it with respect to dynamics, but your intuition is absolutely correct that as you train, correlations will develop between the parameters that break the IID property and therefore violate one of the assumptions of the central limit theorem.
Yeah. So let me just say one thing. This is related to the thing I asked you earlier about, sort of self-averaging, because in some universe you might imagine, there's a unique best set of parameters. So no matter where I start in some, landscape, I'm going to flow to that. So then I develop infinite correlations, right? Which is the perfect correlations between, even though so in some landscape I'm flowing down, I start at arbitrary places, but always flow to the same deep minimum. So that's one sort of extreme picture I might have in my head of how the process goes.
That is the thing that you hope for. That
Right.
The dynamics uniquely leads the infinite ensemble of neural networks to a single neural network that perfectly solves the problem. But in practice, that's not what happens.
Right.
And so one of the bits of the story, including the theoretical toy models, is precisely the fact that the training does not converge the neural networks to a unique function, but rather there's some variance that is important to estimate.
Great. Thanks.
Sure. Okay. Let me mention non-Gaussianities and then mention dynamics. I am. What time should I really end by? We started 10 minutes late.
Yeah, I think it's 40 past.
40 past is fine. Okay, good. Now I'm going to mention briefly, and I'm going to say I can really punt some of this to Friday, so I can address that now. So, good. So since I keep mentioning them, I'll write it on the board. So I wrote these lectures. If you're curious about the examples I'm mentioning, TASI lectures on physics for ML. If you Google that, it should give the relevant hit. And these lectures are an adaptation of that, and I'm producing a similar PDF because I already had it and can adapt it easily. And so the examples I'm about to mention are in those notes. Yes.
Great.
Yes.
Just a question about the one of our expansion.
Sort of
Discussed this with you. Maybe one thing.
So what expansion are you talking about?
The one of our expansion.
But I haven't introduced one of our expansion yet.
Oh, okay. Maybe I'll ask the question when you get to the one.
See what I did?
Well, you did 2.1. Yeah.
I'm no, I give you a hard time because I'm literally going there. So like ask me your question in 5 minutes. Yeah. Okay, good. So good. So all I want to do in the final bit of this statistics section is talk about non-Gaussianity. And there's much more to say and many details. Or if you'd like, if this is a Gaussian process, then this is a non-Gaussian process. And the essential idea, since I'm a little short on time, and we'll cover some of this in a couple of days, is that if Gaussianity in your theory is from a central limit theorem, then violate the CLT assumption. This implies, in general, non-Gaussianity. And so crucial assumptions. Maybe I'll mention this one first because it already came up, not this one, but I'm not going to have too much to say about this today. There's an independence assumption, right? And so if IID is part of the assumption that makes the central limit theorem hold, and you understand why you have the IID assumption, then I actually don't know if other communities do this. In high energy physics, if we want to talk about breaking something, we write the word and we draw a slash through it. Okay, so IID breaking is going to be something that in principle introduces non-Gaussianities into the theory and slightly breaks the Gaussian process. And to give you an example of that just in words, if I have some weights that are relevant for the IID Gaussian story, and they're just multivariate Gaussian weights, e to the minus half xi, sum on I, turns out you can factor that into a product, it's independent. But the second that I introduce a quartic, lambda times xi quantity squared, I can't do that factorization anymore, and it's breaking the independence. So that quartic deformation of the Gaussian on parameters is introducing, that parameter independence breaking is introducing a non-Gaussianity into the function space that is giving non-Gaussian statistics to the functions themselves. So IID breaking. And to Kit's question, n goes to infinity is also part of the central limit theorem, right? So 1 over n corrections. Namely, if you don't take, so if you assume, for simplicity, putting the assumptions aside and having only one violated, if I have IID, but I'm at large but finite n, I don't have the central limit theorem, and I should be able to measure the non-Gaussianities in a 1 over n expansion. And the simplest way to do that is to use something called the connected correlation function. I'll actually put 2n in there. And it turns out when you study the connected correlation function, under the central limit assumptions, you take n to infinity and then you back off. The question is, how does the connected correlation function scale with n? And it scales as 1 over n to the n minus 1 under standard central limit assumptions. This is how connected correlators behave. Let me say more about connected correlators. There's a couple of facts that you need to know. In statistics, they're called cumulants. So these are not moments. Moments are the correlation functions. These are cumulants, the connected versions thereof. In quantum field theory, one of the first calculations you do in phi-4 theory is compute the tree level diagram for 2-to-2 scattering in phi-4 theory, and you have this tree level diagram. That leading piece is the connected piece. What the connected correlators don't have is the disconnected pieces that are products of lower point functions. So in particular, the 4-point function, the connected 4-point function is the 4-point function minus the products of 2-point functions plus permutations. Okay? And so that object, and the final point that's really crucial, Gaussian theories don't have connected correlators above the 2-point function. So all of the connected correlators have better vanish in Gaussian theories. And so if you have 1/n corrections that are signaling non-Gaussianities, you should see it in some 1/n expansion of the connected correlators, subject to the constraint that the higher things had all better vanish as n goes to infinity because it's recovering Gaussianity. So this is something that is known. This is in the literature in various places. Zohar has worked with it. Shoyaida and Boris Hanan have done this. My group has done this. There's different versions of it in different contexts. But the essential bit is that if Gaussianity is coming from a central limit theorem, then you get non-Gaussianities, which are interactions in the field theory, by violating some assumption of the central limit theorem. And so you can choose different ways. I'll leave the non-Gaussianity bit there so that I can get to dynamics.
Well, I just it was like a really stupid physics question. But,
Sure.
In physics, it's true for vector models, say, but if you have like a large N limit, half limit or so, you've got different, you have different large N limits. So.
Yes, double scaling.
Yeah.
Yeah, that's true.
I mean, no reference to what you say, but
Yes.
then all the higher order curves.
There are different limits and you have to be careful.
Yeah.
You invited the question. Boris is going to be here tomorrow. And one of the things that Boris has worked on is an L/n expansion, where L is depth and N is width. And in this line of work, they want to take both large, but they want to take L/n fixed, which is one of the double scaling limits. Different context, but it's similar in spirit.
Maybe I have to ask a question.
Yes, now ask your question, since I set you up. So everyone, this is what Kit was asking about, any question?
So there's this sort of maybe slightly useful way of thinking about the action as a think about it as a measure on function space,
Yes.
right? Induced by the initial measure you start with on parameters.
Yes.
And clearly for any finite n, the result you're taking a finite dimensional space and measure space and you're putting it into an infinite dimensional measure space, i.e. function space. So for any finite n, this will have low dimensional support and will be basically singular when you embed it into function space. So it's like a weird object sitting inside infinite dimensional.
From the point of view of a function space density and the support it has in function space.
Yeah, exactly.
From the point of view of parameter space, it could be very vanilla.
Right.
Yes.
Exactly.
Yes.
Yeah. So then there's thing is we're in the math part. So for infinite n, it's clear that it becomes the smooth, Gaussian process. It seems to me that in order to capture the finite n behavior in a 1/n expansion, you would need to take all orders in n and resum, because you need to end up with some singular behavior at the end. How should we?
Yeah. That might be the case. I don't know for sure if it's the case.
I think it sort of has to be.
So what do you mean singular behavior in terms of how it's embedded into function space?
Yeah, you have to reconstruct a lower dimensional measure from a sum of it over infinite.
It is true. It's a finite dimensional function space. And so you do need to have some unusual embedding that the embedding is implicitly.
All of the elements of the 1/n expansion, those are all infinite dimensional. So you're taking all these infinite dimensional guys, summing them up, resumming them into a singular finite, low, like finite dimensional thing at any finite n.
Yeah, I mean, I guess I don't have anything useful to say on the resummation. I don't necessarily disagree with what you're saying. Zohar might have a comment. One thing I will say that I do know, not about the resummation, is that something you can do is you can compute order by order in 1/n the corrections to the action, which is something that
right. You have to sum up all of those to get the actual action at finite n.
Yeah, I mean, you're asking the question: to what extent can you trust the truncated action relative to the true action?
Right. Given that it's this weird.
I guess I don't have a sharp answer on that about how faithfully that's the question. How good is the approximation of leading order or next to leading order in 1/n relative to the ground truth? Zohar is raising his hand and has worked on this, so maybe you have a comment.
It's a great question. It bothered us as well. You can think about that as a way of regularizing the theory, right? We have different K space. And indeed, when we did this perturbative analysis, we were worried how all this integrated part of the function space would it work well. So we had some thoughts that it might not. And eventually, in a rare case, you see that you do the expansion in 1/n, n orders in 1 over n. So the leading order in 1 over n does work. The only comment is that it's not really 1 over n, it's more like number of data points over n.
That's
The more safe small parameter to take from.
But even at initialization, you
No,
want
not
to.
in it. I talked about.
During training, okay.
They say that, but initialization.
Right.
You would also, I mean, it depends what you calculate then, but as long as you calculate low order functions. I mean, one way to think about that is a non-definition. As long as you calculate low order correlation function, you don't know these problems. You can sort of marginalize all the other points, and then you do have enough parameter to spend any function of like 6 points or 10 points. So
1,000 parameters in this large. Can I just ask, when you say number of training data points, do you mean the number of training data points factor or correlated, or the actual size?
Well, it's related, but I was thinking about actually the number of data points you are training on.
Okay.
Yeah.
So the case of the mechanisms and sorry, this one, the physics. To generate finite dimensional measurements. Like for example, if you homomorphic localization in supersymmetric field theory or something, you design finite degree curves.
Yeah, all very good questions. I actually want to move on to dynamics. Maybe my final comment on these questions is that these are questions which you can ask experimental questions about, which is what Zohar is saying, like try it, see how it works. You know, measures on function spaces and, you know, associated correlators in field theory is part of the thing mathematicians notoriously complain about. They will tell you, for example, phi-4 theory in 4 dimensions in the continuum does not exist as a theory. And then, you know, as a physicist, you say, do I care? I just put it on a lattice, and that obviously exists. So I don't know that anything that I'm going to say in these lectures or any thoughts I currently have are going to solve the deep pressing questions of axiomatic field theory. The question is a valid one. I just don't know the answer. But part of the point is that the neural network description sort of simplifies things in the sense that these integrals and these correlations are very obviously, I think, well defined, at least relative to standard Feynman path integrals. So Kid, I know that's not satisfying, but you know that's sort of the current status, and I refer you to Zohar's paper. But one other thing that I want to say is that something that when you do compute these 1 over n interactions, in general they will be non-local, and there will be some scale of non-locality set by the hyperparameters in the problem. So when you do that 1 over n correction and you pick out the quartic interaction associated with these 1 over n corrections, it is not true necessarily. It can be, but it doesn't have to be integral lambda phi of x to the 4th with the same x for all of them. So that's part of the story, is that somehow the non-localities are intrinsic to this, and the question is whether you can understand them, control them, etc. Yeah, a final question that I really like. I have a whole nother section to this talk. Yeah. Oh, I'm going to dynamics in just a second. Yeah. Because you want to do backprop and do training.
What's the relation?
Yeah, I mean, d phi by dx is the variation of the derivative of the network prediction.
I have the action, I can do the variation with respect.
Oh, I'm sorry, you're talking about d phi in the action.
Well, if you consider the variation with respect to phi, you have to consider.
I mean, it is true that d phi as an object does appear in the action in general. It's part of the story. You can, alternatively, if you just want to compute these correlators, you can compute correlators involving derivatives also. You don't just have to compute the correlators of phi, you can compute correlators of d phi by dx and so forth. There are other correlators that exist in the Gaussian theory. The theory is Gaussian. Sometimes the Gaussian theory implicitly has d phis in it, and there are Gaussian neural network theories that are known to recover the free scalar, in which case there better be d phis, right? Integral d phi is the free scalar. And so there are other correlators. It's just a different local operator, and you can consider those correlators. d phi by dx is very relevant for learning, as we're about to talk about. But from the point of view of the ensemble is the ensemble, and if you choose to compute expectations of derivative operators, that's something you can do. That is a totally different topic, which I invite you to ask me about offline in the interest of time. In many cases, the actions are computable. The questions about the equation of motion is sort of perpendicular question.
Yeah, your 2 point, the point is actually your 2 point correlation on the top there is very non-local.
Yeah, that's right. A priori, it's non-local. Yeah. I want to say something about that. And my time is up, so I better be brief. Okay. I guess this is turning into dynamics 101. And I really appreciate all the questions. Great that people are so interested in statistics. The dynamics story sort of goes like this. A fundamental question that is an order one question is how does the neural network evolve under gradient descent? So I am going to be in a supervised setting for simplicity. This is the most vanilla setting. To remind you, I have D of X alpha, Y alpha. Alpha runs from 1 to D. This is the train data. These are the labels. Indeed, these are exactly the Y's that are not the Y's that I was talking about, the correlators. These are the labels. These are these objects are living in R D times R in the scalar case, where Y alpha is a scalar and X lives in RD. Yeah. And in this setting, I have some loss function, which again is depending on the network. Divide by the number of data points. Loss phi of X Y alpha. Okay. Some element Y is loss. And then gradient descent. Gradient descent is the statement d theta I by dt is equal to minus some learning rate gradient of the loss. And I'm going to have some other definition that's going to be relevant in a moment, which is to find this delta of x to be dl of phi of x comma y by d phi. So this delta is dl by d phi. And so looking at this d theta I by dt can be rewritten as eta under the gradient descent assumption. This equality is assuming, sorry, this is gradient descent. What am I doing? I'm doing a chain rule, is what I'm doing. I'm doing a chain rule, the signs from there. So I'm doing a chain rule. Sum alpha equals 1 to d, delta of x alpha, d phi x alpha by d phi I. Okay. So so instead of just dl by d theta, which is what gradient descent would have given me, I have dl by d phi by d theta. And now I introduce the final formal object. Okay. Oh, now. Oh, I guess my luck's run out. I will introduce the final formal object of this first lecture, which is something called the neural tangent kernel. And I will make, in the interest of time, I will not do the calculations that are in the notes. I will make the formal points about it. So this is the neural tangent kernel. Okay. So the question you want to ask is how does the neural network evolve in time? Phi of x is the neural network prediction. We want to d by dt it. This is d phi of x by d theta I, d theta I by dt. But now here's where I'm going to write gd over the equality. Now I'm going to assume gradient descent. That I update my parameters according to gradient descent so that d theta I by dt is negative gradient of the loss. And I get eta over data set size sum alpha equals 1 to d. There's an extra chain rule involved. It's literally just chain rule. And crucially, I have this object, theta of x, x alpha. So here, this is how the network is prediction is evolving on any test point x. The x alphas are in the train set. And this object here is d phi x by d theta I, d phi x alpha by d theta I, sum on I implied. And this object is known as the neural tangent kernel.
That's the time.
Yes, I'm going to come to that. We're anticipating the key point. And okay, so let's look at this object. This object, so this is DL, this delta is DL d phi. This is how much the loss varies as the network prediction fluctuates. Yeah. And what this object is doing, just looking at it, this is about the time evolution of any point x in the domain. This is summing over all of the data. This just depends on the data and the loss and the fluctuation, but this does not depend on x, this just depends on x alpha. And so the role of this object is to take information about the loss and the function and the prediction at x alpha and communicate to x, right? And so this is a fundamental object that is appearing in a 3-line derivation or something like that. This is work from around 2018 by Jacob et al. Some other papers had similar ideas in the air at the same time. And this is fundamental, but it's also unwieldy. And what do I mean by that? Well, it's parameter dependent. So this sum here is a sum over all the parameters in the neural network. I just got a beefy laptop, and my beefy laptop can handle some of the open source large language models. Llama 3.3 has 70 billion parameters. And the bigger, the ones that are ChatGPT has more. Okay, so billions of parameters. So good luck doing that computation. It's time dependent. Because it's parameter dependent and the parameters are evolving, it's time dependent. And it's stochastic in the sense that we mean sort of throughout that the evolution of this neural network depends on the initial draw. And so there's some randomness coming from the initial draw, and that sort of plays a role in the trajectory. And so even though it's fundamental and emerges as a fundamental object that tells me how things happening at x alpha get communicated to updates at x, yeah, it's very nasty to deal with in general. And obviously, I'm telling you this story for some reason. Am I unlucky on this part too? Yeah, I guess by translation is very I am. So there's a reason that this is a classic result, and it was alluded to by Zohar. And indeed, there's a lingo thing that I can talk about in a second. Some people, well, I'll address it in a second. He asked whether I'm talking about the time-dependent thing or not. I am talking about the time-dependent thing here. But in the n goes to infinity limit, there exist simplifications under reasonable assumptions. It doesn't always happen, but it often happens. What happens, one of the things that happens is that you're in what's called the lazy regime. We can talk about how you feel about this in a minute. That theta of t minus theta of 0 is much, much less than 1. Namely, as n gets big, the parameters are barely moving. So there's a lot of them, but they're barely moving. They're in some local neighborhood of their initial points. It's called the lazy regime. If your parameters have barely moved, it suggests Taylor expanding your network in parameters in the limit sim equal to, the neural network is close to a linearized model, which is defined to be phi of theta at initialization plus theta minus theta 0, I d phi x by t theta I evaluated at initialization. So this is the linearized model, and the lazy regime is the statement that as n goes to infinity, because the parameters are barely moving, you can approximate the neural network by a model that's linear in parameters. It's still nonlinear in inputs, but it's linear in parameters. And because of this, when you look at this NTK, what you find is that the neural tangent kernel associated to this object becomes approximately equal to the neural tangent kernel at initialization, because the model is close to the linear model. You d by d theta, it gets rid of the thetas, and then you're just evaluating everything at theta 0. And so this is a simplification. This is the fundamental object that is sort of governing the dynamics of gradient descent. In a particular limit, it behaves very well. And this thing, in general, this is the simplifications. It's time independent. And there's even a case where by the law of large numbers, you can write it as an expectation value of some other object, p of theta 0, some other object that I don't have to worry about. And this means you can compute once and for all. Say it again. There's two steps. One is that you're close to the linear model. Because you're close to the linear model, this MTK that governs the dynamics at large n becomes equivalent up to some, the rigorous papers approximate the error. It becomes equivalent to this initialization neural tangent kernel. And then this object, when you study what's happening when you write down an equation for this object, you realize eventually that there's 1 over n times something that's just repeating, and you're taking n to infinity. Those things are independent, and so you can use the law of large numbers by replace it by a mean of some appropriate object, such that you can just compute this. And so for many different architectures, this thing is just computed once and for all, and you have a fixed closed form function that governs the dynamics, which seems like a priori seems great, but it feels like there's got to be something hiding under the rug. This life can't be that easy. Five more minutes to make my point. Okay. So this thing becomes time independent and some fixed deterministic function that governs the gradient descent dynamics. But the complaint well, there's a lot of them. That a fixed theta that doesn't evolve, that is just gives some kernel that's interpolating between train points and test points where you're wanting to make predictions. That's true. And in particular, there's no learning. There's no learning in the traditional sense, because you're integrating out all the parameters. And it's the initialization thing. It doesn't have any parameters in it. It's just some fixed function. There's just some kernel that is determining the neural network prediction. So there's no parameters that are updating. And so under what we normally mean by neural network learning, there is no learning. The parameters don't move, and in particular, you can, by an appropriate calculation, completely get rid of them. And even though these are valid complaints, there is a toy model that I detail in the notes, where in this toy model, you can additionally assume, and this was, I think, what Zohar was getting to, if you have that the loss is equal to mean square error loss, you do everything else the same, but you assume mean square error loss. What you can do is you can solve a Diffie-Q for the neural network dynamics exactly. And there's formulas in notes. I think this arises in a number of places. There is a beautiful paper by the Google group that I have in mind that I learned this from called Wide Neural Networks of Any Depth Evolve as Linear Models Under Gradient Descent. It's a great paper. And in this paper, they solved the differential equation for the neural network dynamics exactly. There is no learning. It just uses this kernel. It is equivalent to kernel regression. It is equivalent to kernel regression, which you might be familiar with, but the kernel regression does not involve any neural network parameters. With respect to a fixed kernel, the NTK. And the final point I would want to make about this, because I advertised at the very beginning, in particular, these papers have an equation for G1 infinity of X, which is the expected value. I'm going to write it because it's so absurd. The expected value of an infinite number of infinitely wide neural networks. Sorry, not number wide, infinitely wide neural networks trained to infinite time. There's three infinities there. It's a toy model where you have an infinite number of infinitely wide neural networks trained to infinite time. They did not put it on a computer. That turns into a black hole. Instead, a different duality frame opened up. The dynamics simplified. They solved it, etc. And so this is a remarkable, like this is one of the main things you would be after in ML. And yet these complaints are completely valid. You have this wonderful toy model that doesn't learn anything. And actually, you can, of course, this is equivalent to kernel regression. You can ask, how well does it do? And there's a nice paper by Google doing the empirics of this versus other cases. And sometimes it actually does decently well, but it's actually just kernel regression. And so the final point that I want to make, and this will really just, I guess all of this just set up for us, and maybe Zohar also, and maybe others, I hope. This is the essential point, that all of these results, this was an extra assumption, but all of these results came from this point, that I'm in the lazy regime. And we say, if parameters don't move, we say that we did not learn features. Which brings me final point, which is feature learning. This is a story in the literature that many people have contributed to. The question is, well, there's a lot of questions. There's principles by what you mean of it. But some of the principles that were laid out nicely in the literature and also in some lecture notes by Cengiz Pehlivan and Blake Bordelon is to basically ask, how do we avoid this? And when you study why did this happen, why do the parameters not move at large n, you might imagine that you just study how the parameters and how they update scales with n. And if it scales as 1 over n or 1 over n to some power and goes to infinity, they don't move. And so this is, if you'd like, this is principles for n scaling. That what you want to do in your architectures is the following. I'm going to use some lingo here. So you want finite initialization reactivations. Reactivations. Okay, so that's principle 1. Maybe I'll even give it a 1. And what I mean by that is that the pre-activations are order 1 in n for all the layers. So concretely, what this lazy regime means, like in a deep network, you have the pre-activations and they go through the activation function, they turn into post-activations, then you move to the next layer, right? The pre-activations, you find that they're actually not moving. And so the way that you do this is you have principle 1 and you demand under principle 1 that the pre-activations don't go like 1 over n to some power, in which case they won't move as n goes to infinity. And they don't go like n to some positive power because then they'll blow up. You want them order 1 in n. The second principle is finite learning time. By which I mean that the update to the network prediction by dt goes as order 1 and n. But the third principle is that you learn features.
Got it.
Which is that dz by dt. These are the pre-activations, this is order 1 and n. And so what you do in your architecture, you do a theoretical analysis. You introduce 1 over n factors with exponents that you can vary. So you parameterize your independence as 1 over n to some power in various different places. And then you do this analysis and you demand that all of these things are true. And you can see what constraints that puts on the exponents in your n expansion. And then you try to solve the constraints. And the one result is that if you make one additional assumption, there exists a unique solution for deep network, for feed-forward networks. And it's called mu p. But more generally, the principle holds that these are just principles that you would want to ensure that as learning is happening, the things you care about, the pre-activations, the features, the network prediction, that nothing blows up in n or shrinks in n. And so you just parameterize your ignorance in n in your architecture, and you do a calculation, and you try to see if you can solve the constraints. That's my understanding of literature, at least. So thanks a lot. I'm very sorry that I went over by 20 minutes. I started 10 minutes late.
So there is a second chance to meet Jim on Friday. I'm going to be, and I think your point will be to bring the discussion back to physics. But if it's, am I right to say it? What?
Yeah, this was field theory for ML, and on Friday I'll do ML for
Okay. That might be useful. You have the lecture notes that I see you following.
Yes.
Yes. So the lecture notes will be on the website.
I can polish them a little bit and give them to you. They will not be finalized until next week, but I can definitely give a polished version and just send them to you.
If somebody wants to get a preview, they can look at your.
Yeah. So the Tazi lecture note, Jim Halverson, you'll find them on the archive.
All of this content is there. Yeah.